All right, everyone, Mr. Graham here. Today I want to talk to you about the derivative. Yes, the derivative is a calculus concept. We are going to cover the derivative in AP Physics C long before you actually cover it in your calculus class. So keep that in mind. I'm not going to go through nearly the rigorous detail that your calculus teacher will. And I'm going to give you some rules that are going to make the derivatives that we need to do very soon a lot easier than doing it the long way. However, in your calculus class, you're going to have to do it the long way. You're not going to be able to use the rules that I teach you today until your calculus teacher lets you know what those rules are and allows you to use them. So please keep that in mind. Don't get me in trouble with your calculus teacher. You'll just annoy them. To start our discussion of the derivative, what I want to do is first get my mouse. I want to show you why the derivative is so important in our study of physics, and the reason that we're going through the learning about the derivative so early on is because it's essential to studying motion at a higher level. At this point, we've really just covered uniformly accelerated motion or motion at constant velocity. What the derivative will allow us to do is to study non-constant accelerated motion. So if the acceleration is changing, and realize that the acceleration is just the rate of change of velocity, and velocity, just like the velocity is the rate of change of position of an object. And so the derivative is all about rate of change. It's all about rate of change. It's all about slopes on graphs. You know that the slope on your normal y-x or xy axes, the slope of a line on those axes is the rate of change of that function. Okay, so I want to start by just reminding you should know this. You should be very familiar with what uniformly accelerated motion looks like on a position time graph. I'm going to generate a position time graph for uniformly accelerated motion just with the cart sliding down the ramp here. I could even go up and down the ramp. You should know this at this point, I should get a nice parabola. And sure enough, that's what I get. During the motion, I have a nice smooth parabola. If I just start from up here and don't push it up the hill first, then I get a half parabola. And if I auto scale that, it looks pretty linear, but that is a half of a parabola. Let me try to do that one more time. Get a little more curvy looking. There we go. That's a pretty good parabola right there, a half parabola. If I were to do curve fit here, the best fit curve would be a quadratic. Okay. Now the thing is that this is a position time graph, so the slope at any point on this curve would represent the velocity of the object. But because the slope is changing as we go along the curve, that means the velocity is changing. Obviously it should be, because the object is accelerating. It's speeding up on the way down. So this is the type of graph we're actually going to consider when introducing the derivative. Okay. So I'm going to leave the realm of physics for now. For now, we're going to not talk about physics. We're just going to go back to just talking about pure mathematics to define the derivative, and then we will apply the derivative to our study of motion. So I'm going to go ahead and just draw my xy axes. So we've got my y-axis, my x-axis, and I'm going to draw a curve here. I'm just going to draw a parabola. We'll go with the parabola. I'll have a non-zero y-intercept. And realize that the slope of this line at any point tells us the rate of change. If this was a position time graph, the slope at any point would tell you the velocity. So if this was a velocity time graph, we start with zero slope, meaning zero velocity, so the cart starts at rest. And as it slides down, the slope gets increasing, it starts increasing. The slope of the line actually gets steeper and steeper. The velocity is increasing, as we should expect. Now, when I'm talking about the slope of a point, or the slope of the line at a point, I'm talking about the slope of a tangent line, right? Not tangent as in SOHCAHTOA tangent, but tangent as in what you learned about in geometry. So if I want to know the slope at, say, this point, then I would have to draw a tangent line to the curve at that point. The slope of that tangent line would represent the slope of the curve at that point. And again, if this was a position time graph, the slope of this line would tell you the velocity of the object at that particular point. Okay? All right. Now, before the invention of calculus, a guy named Isaac Newton and another guy named Leibniz actually invented calculus independently at about the same time. But because Newton was so much more famous, we tend to give credit to Newton, even though it was two people that invented it. Before calculus, though, you could only approximate the slopes of lines, of curved lines. And they would approximate them by choosing not one but 2 points on the curve. So say these 2 points, and to find the average rate of change or the average rate or the average slope between these 2 points, we would draw a secant line. A secant line is a line that goes through 2 points on a graph. So this would be the secant line between those 2 points. And let's say I wanted to determine what the slope of that particular line is. We use what is called the difference quotient to calculate that slope. And I'm going to label some points here. Bear with me as I do some labeling here. I'm going to label a couple points. This first point I'm going to call X. And then the second point I'm going to say is at a distance delta X away, final minus initial. So this point is going to be X plus this distance delta X. Right? If this was 1, if this X equals 1 here, and the distance was 2, this would be X 1 plus 2, so this would be X coordinate 3, obviously. But to generalize this, I'm not going to use numbers, I'm just going to use the symbols. Now, if I wanted to know the corresponding Y values, well, I have to remember that this blue line is a function. The function, I'll just call f of x at this point. This function, evaluated at this X coordinate, will give us the Y value. And so based on what I have here, that would be f of x. Our y coordinate here would just be the function evaluated at this point x. Similarly, this point would be f of x plus delta x. That's what this says, f of x plus delta x. I have to take this point, which is a discrete number, but I have to write it like this for generality purposes. And that would be f of x plus delta x. And so the slope here, and remember that slope is rate of change, would be rise over run. Well, what's rise over run? You learn in mathematics that it is delta y over delta x, which means my final y value minus my initial y value over my final x value minus my initial x value. Well, my delta y in this case would be f of x plus delta x minus f of x. So it's f of x plus delta x minus f of x. That is just my change in y. And then divided by my change in x. Well, I don't need to do x plus delta x minus x because that's just going to give me delta x. And so in the denominator, I'm going to have delta x. So this would be the slope, again, of the secant line. That's algebra. We can do this with algebra. We can approximate the slope here by just picking another point on the graph and then finding the slope of the secant line. What calculus lets us do is determine the exact slope at this particular point. And to do that, we use what is called the limit process, or we use limits. You might have seen these in pre-calculus. If you've had calculus before, you obviously know everything I'm talking about. But the slope at this point, I need to find the slope of the tangent line at that point. And so to do that, we use, again, what we call the limit. And so if I want to find the slope, the instantaneous slope, sometimes it's called just because it's at this particular instant on the graph, we know the slope of that secant line. The instantaneous slope, that's going to be the slope of the tangent line. That's going to be what we refer to as the limit, and I'll explain this in a second, as delta x approaches 0 of this quantity here, of the difference quotient, f of x plus delta x minus f of x, all divided by delta x. Now, what does this limit mean? Well, we're just saying as delta x gets really, really, really tiny. In fact, I'm going to say infinitesimally tiny. That's a tough word to say, infinitesimally tiny. Infinity is the biggest thing. Infinitesimal is the smallest thing. So we're going to say as delta x approaches 0. We're not going to say delta x is exactly 0. It's just going to be as close to 0 as you can be before it actually becomes 0. So it's, for all intents and purposes, about size 0, but we're going to say the limit as it approaches 0. And you can see, as delta x approaches 0, this distance gets smaller and smaller and smaller. So the 2 points get closer and closer together. as delta x becomes infinitesimally small, we essentially have the slope of the tangent line at that point. And notice that the tangent line here would not be, or the slope of the tangent line would not be the same as the slope of the secant line. Sorry about that. That's why when we use algebra, we can only approximate these slopes. This is the tangent line here. Obviously, that tangent line has a different slope than the secant line. Okay. So how do we evaluate limits? Well, the easiest way to evaluate a limit, if possible, is just substitute the value that delta x is approaching into the equation, into the difference quotient, anytime you see delta x. As you can see, that leads to a problem because we can't put this 0 in the denominator here. There are other ways to evaluate limits. Just understand that your calculus teacher is going to go over those. You're going to be doing limits for quite a while. Here, I'm just going to kind of give you the bare bones idea as to how this works. Okay, so because we can't just plug 0 into the denominator here, we got a little more work to do. And to show you an example, I'm actually going to define my function. Let's say that this f of x is equal to x squared plus 1. It's a nice parabola. And so f of x, as we see it here, is going to be that quantity x squared plus 1. Now remember, when you evaluate a function, say you want to know what f of x is. F of x is x squared plus 1. If I want to know what f of 3 is, that would just be 3 squared plus 1. If I want to know what f of x plus delta x is, which we're going to have to put here, I just plug x plus delta x in for x. So that's actually going to be x plus delta x squared plus 1. Okay. So now we have this discrete function here where you can actually evaluate this limit. And I'm going to go through this as an example. In the next video, I'll do a couple more examples and then give you some rules that'll make this process a little easier. But just so you know, when we do this limit, when we say the limit as delta x approaches 0 of the difference quotient, this is the limit definition of the derivative. Right? In mathematics, we have to have very rigorous definitions of mathematical concepts. In this case, this is right here, the limit definition of the derivative. Now, very often, or not very often, but we have multiple ways of denoting in math language the derivative. One way is dy over dx. And again, just think of this as being the slope. This is just the slope. Dy over dx is just the slope. In fact, as you take the limit, let me put this right here, the limit as delta x approaches 0 of the slope delta y over delta x, this becomes dy dx. So you can think of the d's here, the lowercase d's, as replacing the deltas. Only now those d's represent deltas that are infinitesimally small. So very, very, very tiny, and therefore we can get the instantaneous rate of change. So that's one way of denoting the derivative. Another way, I'm going to show you a few ways that you're going to see derivatives being denoted. Sometimes it's just y prime. It's not a 1, it's like a little apostrophe. Sometimes it's f prime of x. So this would be the derivative of f of x, would be f prime of x. Sometimes you see d over dx of f of x, okay? So when you see it like this, it's like the derivative of this function with respect to x. That's just the terminology. Don't get hung up on the terminology. I'm going to show you in the next video some rules that make this process a lot easier, okay? So what I'm going to do is use the limit definition of the derivative to compute the derivative of this function here. And I'm going to go ahead and erase a little bit so we have a little more room, because the algebra, when we use the limit definition, becomes a little cumbersome and actually will take up quite a bit of space. So again, I'm going to write my derivative, dy dx, will be equal to the limit as delta x approaches 0 of the difference quotient, f plus delta x minus f of x over delta x. And remember, this just means slope. It just means slope. That's all it is. But now I have to actually plug in values for f of x plus delta x and f of x. And again, my f of x plus delta x will be this equation I plug x plus delta x in for x squared, in for x here. So I get x plus delta x squared, and then I still have that plus 1 tagged on the end. And then f of x obviously is just the function itself. F of x is x squared plus 1. So all I need to do is plug these in. I need to plug this in for f of x plus delta x, and I need to plug this in for f of x. And when I do that, I get that the derivative of this function equals the limit as delta x approaches 0. Now, we're not going to evaluate the limit for quite a while, because again, we can't put a 0 in for delta x. Realize that until you evaluate the limit, you must write the limit as delta x approaches 0. If you leave that off in your calculus class, both in your class and on the AP calculus exam, you will lose points. So you need to keep writing this until you actually evaluate the limit. Okay, so f of x plus delta x again is x plus delta x squared plus 1. And then we subtract f of x, which is just x squared plus 1. You got to put it in parentheses because that minus distributes over both terms there. And remember, this is just the rise. This is literally just the rise. All right, we're just doing slope here. And then my run is simply delta x. Again, I can't evaluate the limit because I can't put a 0 in for the denominator here. All right. So my next step, I just need to simplify the algebra here. You'll find that any particular calculus problem in your first few years of learning calculus, there might be 1 or 2 calculus steps and then 15 algebra steps. So your algebra needs to be on point here as we go on in both this class and your calculus class. So that will be the limit as delta x approaches 0. I'm just going to FOIL this. You should be good at foiling at this point. And when I FOIL this, I get x squared plus 2x delta x plus delta x squared plus 1, and then I'm going to distribute the negative over both of these terms, so I get minus x squared minus 1. And all that is going to go over delta x. And you'll see where I'm going here in a second, because now we get some cancellations. I have an x squared, I have a minus x squared. I have a plus 1, I have a minus 1, so all those go away. So in my next step, I get that the derivative of this function with respect to x is equal to the limit as delta x approaches 0 of what I have left over, which is 2x delta x plus delta x squared all over delta x. Now, if you need to factor out a delta x out of the numerator, both terms in the numerator before you can cancel the delta x, that's okay, but I'm going to go ahead and just cancel this delta x with that delta x and one of those delta x's. And I'm left with the derivative of the function with respect to x will be equal to the limit as delta x approaches 0 of the quantity what's left, 2x plus delta x, and nothing left in the denominator. So in fact, I could just write this, 2x plus delta x. Delta x is no longer in the denominator, so now we can just evaluate the limit. And again, to evaluate the limit, I just say delta x is getting infinitesimally close to 0, so I can essentially just plug in 0 for any delta x's now. So I'm going to plug that in, 0 for delta x. I have now evaluated the limit, so in the next step, I need not write the limit as delta x approaches 0 because I've just evaluated it. And so I get that is 2x. That is the derivative of this function. The derivative of f of x equals x squared plus 1 is 2x. Notice it is in itself a function. And again, I could write it as f prime of x. This is another way of denoting the derivative is just 2x. So 2 ways of saying the same thing. Notice x appears here, which means the slope. Remember, the derivative just tells you the slope of the original function. Because this is a function, because if I plug in different values for x, I get different results, that tells me that the slope is constantly changing. If I want to know the slope at x equals 1, so let me write that here. If I want to know what the slope is when x equals 1, then I just evaluate f prime of 1, which is 2 times 1, which is just 2. So if this point were in fact x equals 1, the slope of my tangent line, that slope is 2. At x equals 1, the slope of my tangent line is 2. And you might surmise then that, well, what if I want to know the slope? Let me use red still. If I want to know the slope when x equals 3. So let's say that this point here is 3. Let me erase this original secant line. If I want to know the slope at x equals 3, then that tells me that the slope here, the slope of this tangent line to the curve, it's obviously steeper. Well, to compute that slope, it's just going to be the derivative f prime of 3, which is 2 times 3, which is 6. Right? Obviously, a different slope than we have at x equals 1. So if I was to actually measure this slope here at x equals 3, that slope would be exactly 6. This is using the limit definition of the derivative to compute the derivative. The derivative is itself a function. Notice that for a quadratic, always, the derivative will be linear. And for the most part, if you have, say, a third degree polynomial, like a cubic, the derivative of a cubic will be a quadratic. The derivative of a quartic will be a cubic. It's always 1 degree less on the highest exponent on the x value when you do the derivative. Okay. So that's using the definition of the derivative. Hopefully you got some insight here. If this is confusing, that's okay, because we're gonna do some examples in the next video, and I will actually show you how to use the limit definition of the derivative to do one more example, and then I'll teach you some rules that'll make this process a whole lot easier. But again, you're not going to be able to use those rules in your calculus class until your teacher lets you. Okay? All right, that's about it.